Hello everyone, we are a team of chemical engineering students from Abu Dhabi University. Today we are presenting our research on DOE-driven engineering of electrospun carbon nanofiber and high entropy alloy composites for enhanced electromagnetic wave absorption. Our team consists of three third-year chemical engineering students, Kamarem Zode, Mugde Mabbara, and Ziona Safa, under the supervision of Professor Ioannis Bertikudis, who guided us throughout this research. The problem and motivation. With the rapid expansion of 5G and modern telecommunication systems, electromagnetic wave pollution has become a serious challenge, affecting both electronic systems and potentially human health. However, current absorbing materials are often heavy, rigid, and limited in performance, especially in terms of bandwidth and impedance matching. This motivated us to explore a new approach using carbon nanofibers combined with high entropy alloys. Background study. The key idea behind our research is that fiber diameter directly controls performance. Smaller fibers increase the surface area, which enhances interaction between the material and electromagnetic waves. This leads to better dielectric loss, improved impedance matching, and stronger absorption. Why electrospinning and why DOE? Electrospinning allows us to produce nanofibers with controlled morphology and high surface area. However, the process is complex with multiple interacting parameters. Instead of using trial and error methods, we applied design of experiments approach. This reduced the number of experiments from 32 runs in a full factorial design to only 17 ones, while still capturing interactions and enabling predictive modeling. We systematically varied 5 parameters, including injection rate, voltage, polymer concentration, metal ion concentration, and distance within the following ranges of levels shown on the slide. I will now pass the presentation to Fikra Mariam to explain our experimental setup and methodology.
Okay, in the modeling and the methodology part of this study, we started with including the polyacrylonitrile nitride, the PN, dissolved in the DMF as the polymer matrix or the precursor. Then we incorporated the 5 equimolar metal salts to form the iron, cobalt, nickel, manganese, aluminum, high entropy alloy system. At the electrospinning setup included, as you can see in the picture, it included the high voltage power supply, the syringe pump, and the rotating collector. Then we systematically varied 5 parameters that mentioned earlier to ensure the consistency. The consistency of all the experiments were conducted under the controlled conditions of the up to 27 degrees Celsius and 50 to 70% humidity. This is the overall process of the procedure. And when we model the experiment, or when we designed the experiment, we started with the fractional factorial design, which has 16 runs plus 17 plus 1 center point, in total 17 experiments, to identify the most significant parameters. This reduced the number of experiments while still capturing the important effects and interactions. In the result showed that the polymer concentration and the metal ion concentration are the most significant and influential factors, while we have also another key interactions between the concentration of polymer and the distance and the injection rate and the voltage. And this is importantly detected the linearity of the system. So the linear system is not efficient in this case. So we will go for the second phase, and which included the response surface methodology. We applied the response surface methodology using central composite design to build a predictive model. This model captures the nonlinear behavior of the system and allows us to determine the optimal conditions for minimizing the fiber diameter and attaining the target diameter. The model showed a strong performance and good predictive capability For example, its predicted R square value is around 68%. This model has a good prediction stat, and the model allows us to predict the optimal conditions and the target diameter of any fiber, significantly reducing the experimental effort. The next one is the scanning microscope image micrographs that show different parameters combination, the effect of different parameter combination. Generally, we found three types of micrographs. The first one is some condition had the electrospraying, which is completely wide, and the others are defective fibers, which is spares, and the others, of course, smooth fibers. Now I will pass it to Mingizem to present the validation of results and the final outcomes.
All right. To validate the model, we compared predicted results with SEM measurements. The optimized fibers showed a uniform morphology, and the results matched more or less with the model prediction, as you can see. The predicted one was for instance, in the image we're seeing now, the predicted diameter was 471 and the actual was 430. This confirms the reliability of our approach. We then evaluated the electromagnetic wave absorption using a vector network analyzer. The material achieved, or the sample achieved, a strong minimum reflection loss of approximately negative 33.5 decibel at 9.8 gigahertz, meaning nearly 90% of the incident electromagnetic wave were absorbed. It also showed an effective absorption bandwidth of 2.4 gigahertz, covering approximately 8.8 to 11.2 gigahertz range, which lies within the critical X band used in radar and communication systems. For future work, we plan to further refine the response surface metrology model to improve the accuracy of parameter prediction. We also aim to achieve a wider electromagnetic absorption bandwidth, which is essential for practical applications such as 5G shielding, aerospace, and stealth technology. Additionally, more experimental validation in detailed analysis will be conducted. So to conclude, we optimized Electrospun nanofibers successfully using a systematic design of experiments approach. We developed a predictive model and good quality fibers. We demonstrated a strong electromagnetic wave absorption performance. However, it's important to note that this research is still ongoing and the results presented here are preliminary. Despite this, the work establishes a strong foundation for future development of high-performance electromagnetic absorbers. Finally, we would like to thank Abu Dhabi University and our mentor, Professor Ioannis Zobertikudis, for their support and guidance. Thank you all for your attention. You can contact us through these emails for any inquiry. Thank you.